Включить ключ был еще, да?
Я думала, что
Okay. So we know two intersection indices, and it is easy to find simple recurrence relation which allows one to compute several other series of indices, and such relations are called, the first of them is called string equation. The string equation works in the situation when at least one of the characteristic classes psi enters our integral in degree 0. So what is this notation about? We have psi 1 to the power m1, psi 2 to the power m2, so on and so forth, psi n to the power mn, and here we remember only these powers, not which specific class enters the integral in this power, but only the list of powers. This is because the result is symmetric with respect to renumbering of the marked points. Если мы перенумеруем отмеченные точки, интеграл от этого не изменится. Неважно где, если мы берем psi1 в квадрате или psi2 в квадрате, нам все равно. Нас интересует только совокупность этих степеней. И эта совокупность записывается в индексах m1 и m2. So that if one of the psi classes enters our integral in degree 0, like here we have, then the result is like follows. We can reduce the computation of this integral at n plus 1 marked points to computation of other integrals at m points. M1, so M n minus 1. This simple formula allows one to compute explicitly all intersection indices in genus 0. How it comes? For example, we want to compute some integral over m05. For example, it is psi 1 squared, psi 2 to the power 0, psi 5 to the power 0. That is, it is tau 2, tau 0 to the power 4. Let me instead, okay. According to this formula, we should get rid of the last psi class, psi 5, and subtract 1 from each of the previous ones. But if we subtract 1 from 0, then we obtain -1. And for negative values of the indices, the result is 0. So the only positive result is tau 1, tau 0 cubed, which we already know. This is tau 1, because psi 1 is in degree 1, and tau 0 cubed because all the other classes are in degree 3. And so this is 1. And if we do the same for m0, 5, psi 1, psi 2, psi 3 to the power 0, psi 4 to the power 0, psi 5 to the power 0, which is tau 1 squared, tau 0 cubed, what will be the result? Sorry? Exactly. It is tau 1, tau 0 cubed, plus tau 1, tau 0 cubed, which is 2. And why this equation is sufficient to compute all the intersection indices in genus 0? You see, it can be applied when at least one of the indices is 0. At least one of the psi classes enters the integrand in degree 0. Почему? Почему всегда будет такой?
Ну, на 3 меньше, чем количество.
Действительно. So dim m0 n bar is n minus 3. It is smaller than the number of marked points. As a result, there is always some psi class enters our integrand in degree 0, and as a result, we can compute tau m1, tau mn under the restriction then that m1 plus mn is equal to n minus 3, to n minus 3. This is just the multimonomial coefficient n minus 3 choose m1 mn, which is n minus 3 factorial divided by m1 factorial mn factorial. So we know already a huge amount of intersection indices, but all of them are related to genus 0 case. Nevertheless, in higher genera, we are also able to eliminate all classes that enter the integrand in degree 0. The second useful equation is what is called Dilaton equation. Dilaton equation allows one to get rid of a class entering the integrand in degree 1. And this equation reads This is 2g minus 2 plus n times t1 time. It's even simpler. We can get rid of classes entering. We can get rid of classes entering the integrand in degree 1 for the price, which is the Euler characteristic of the fiber here. This is a negative Euler characteristic, 2g minus 2 plus n. This is the Euler characteristic of the punctured surface. And together, these two equations yield all we need some initial condition the intersection index of tau 1. This is the integral over m11 of the class psi 1. And you remember that this m11 bar is an orbifold rather than a manifold. That is why here we obtain a rational number rather than an integer like in genus 0 case. All the intersection indices are integers because all the moduli spaces are complex non-singular varieties. They are smooth varieties. And here we have an orbifold and immediately obtain the intersection index 1, which is rational. Knowing this intersection index, knowing the string and the dilaton equation, we are able to compute explicitly all the intersection indices in genus 1. All intersection indices. Why this is the case? Can be computed.
You have exactly you have dimension.
Mm-hmm. Yeah.
And
Dim M1 n is n. Since the dimension of M1n is n, each non-zero integral over M1n bar contains either some class in degree 0 or a class in degree 1. So either the dilaton or the string equation can be applied from string and dilaton. And it is a final step. We are unable to move further. Neither string nor dilaton equation says anything about higher genera. And Witten's conjecture concerns exactly the higher genera situation. In order to formulate it, let me introduce generating function f in infinitely many variables, which is the sum of, so we have tau 0 to the power k0, tau 1 to the power k1, tau n, tau n. I don't know what is the correct index here. Let it be tau m for the moment. Km k0 to the power k0 or k0 factorial, t1 to the power k. Let it be like that. No. k1 factorial and so on over all possible values of k0, k1 from 0 to infinity. So we consider a power series whose coefficients are exactly these intersection indices. Let me write out a few first terms so as to, it does not seem to be very complicated or dangerous. It does not look dangerous. For example, knowing that the intersection index of tau 1 is 1 over 24, we simply write 1 over 24 t1. It's all rather simple. Then 1 over 6 t0 cubed. You remember that tau 0 is tau 0 cubed is 1, and we must divide by the factorial of the degree, and so on and so forth. Plus 1 over 48 t1 squared plus 1 over t0 t2 plus so it is a huge function, but with relatively simple coefficients, which are rational numbers.
Tau 0 or t0?
This function is a function in variables t0, t1, and so on.
Yes, but in the last line.
Here t0 cubed. T0 cubed, this is in charge of tau 0 cubed, tau 1.
So we basically have all the integrals just divided by the right factorials.
Yeah, but by factorials you divide. In fact, this product of factorials is the order of the automorphism group of the permuting marked points with carrying the same power of the psi class, and so on. And finally, let me introduce the function u, which is the second derivative of f over t0 squared. And the conjecture asserts that this function satisfies the Cartevec-de Vries equation. du with respect to d2 is du dt 0 and 12. This is how Witten's conjecture is. Why it is related to our problem of computing this intersection indices? You see, what is the nature of the string equation? We have n plus 1 mark points, such that at one of them, the psi class enters in degree 0. It does not participate in the integrand. And in this case, we have 3g minus 3 plus n equals m1 plus mn plus 1, yeah, plus 0. We have n plus 1 mark points. And if we eliminate one mark point and subtract 1 from one of the indices, then we obtain g equal to the same value of g. The genus does not change. We have one mark points less, but the sum of indices also is diminished by 1, is decreased by 1. So the string equation preserves the genus, preserves genus. The same is true for the dilaton equation. We have one mark point and the degree of the psi class at this mark point is 1. When we subtract, when we eliminate this mark point, the sum m1 mn will be 1 less than this sum here. And also we have one mark point less than it used to be, so the genus remains the same. Both dilaton and string equation preserve genus. In contrast to this equation allows one to express in terms of those in smaller genera. These equations give us an induction base. We know all the intersection indices in genera 0 and 1. And this equation reduces intersection indices to smaller genera if we start with intersection indices in high genera. Together, they provide a complete set of equations which allow at least potentially, to compute an arbitrary intersection index. The reason why it works is this term. This is a nonlinear term. It is quadratic. It is a product of this function by its derivative. You may consider, you may treat it as a derivative of u squared or whatever it is. The main point here is that it is a quadratic term, rather than linear term. Our differential equation is nonlinear. I will not explain in detail why this equation reduces this computation to smaller genera, but let me say where this equation comes from. It is called a shallow water equation. Значит, уравнение мелкой воды. Знаменитое уравнение Картевега-де-Фриза, уравнение мелкой воды. Оно описывает колебания волн в колебательные процессы в потоке с узким слоем воды. So it is a rather strange situation showing that some combinatorial or geometric or purely geometric or algebra geometric objects can be described with equations showing with equations firstly aimed at describing я забыл, как по-английски колебаться. Колебательные процессы. Yeah, and Witten formulated his conjecture on the physical level in the following form. The A and B models of two-dimensional quantum gravity are equivalent. Whatever this means. Что? Квантум. Значит, две модели квантовой гравитации, А и Б модели квантовой гравитации эквивалентны. Значит, к моменту, когда Виттон формулировал свою гипотезу, было известно, что А модель квантовой гравитации подчиняется двумерной квантовой гравитации подчиняется этому уравнению, а из того, что вот то, что мы с вами обсуждаем, индексы пересечения пси-классов на пространствах модулей стабильных кривых, это B-модель двумерной квантовой гравитации. И из того, что эта B-модель тоже подчиняется этому уравнению, следует, что эти две модели это на самом деле одинаково. Let me say just a couple of words about the A model. In the A model, a two-dimensional hyperbolic surface is obtained by gluing small regular triangles. The number of triangles increases, they are small, they are and we are trying to enumerate triangulations of the surface as the number of triangles increases, goes to infinity. Значит, давайте я словами скажу, потому что по-русски в смысле, что, потому что я боюсь, что по-английски, особенно учитывая мою физическую неграмотность, это будет не слишком понятно. Значит, in string, в теории струн частица считается очень маленькой окружностью. Эта маленькая окружность эволюционирует со временем, образуя двумерную поверхность. По мере того, как с этой частицей происходят разные физические события, она может сливаться сталкиваться с другими частицами, она может расщепляться и так далее. Значит, вот ее линия жизни или поверхность жизни превращается в двумерную поверхность. И на этой двумерной поверхности есть естественная метрика, которая является гиперболической. И считается, что разбиение поверхности на маленькие треугольники хорошо приближает случайную метрику. Если мы берем случайное разбиение, то такое разбиение хорошо приближает случайную метрику. Вот. А это алгебраические кривые и пси-классы в отмеченных точках – это другой способ приближать случайную метрику. Вот. Оказывается, гипотеза Виттона состояла в том, что эти два способа одинаковы. Что...
На каждом треугольнике у нас метрика того самого треугольника.
Да, она плоская, но когда они вместе склеиваются, там возникают особенности. Если вы в вершине вы не можете везде склеить 6 треугольников, потому что у вас получится плоская поверхность, а вы не можете. Плоские поверхности не бывают высокого рода. Поэтому у вас есть особенности, которые соответствуют вот этим самым отмеченным точкам. Я несколько огрубляю, но там формулировка гораздо более точная. И вот для этой модели было доказано выполнение этого уравнения. И поэтому Виттону хотелось, чтобы эта модель давала то же самое. Оказалось, что это так. Окей. Let me stop. Let me stop this physics discussion and let me say just a few words about history. Proving this Witten's conjecture was awarded by few formulating and proving this Witten's conjecture was awarded by few Fields medals. I don't remember Witten. Zankantsevich. then Okun-Kov, then Mirzakhani, let me go back. This is 2010. This is 2006, I believe. Kontsevich probably 1998, something like that, and Witten probably 1990, something like that. So a lot of people gave different proofs, and my goal for today, in addition to formulating this conjecture, is to explain Maryam Mirzakhani's approach to its proving. Unfortunately, she passed away rather young, but she managed to make an extremely significant contribution to our understanding of various aspects of geometry of moduli spaces. And окей. Что? Да, конечно. Okay. So, Maryam Mirzakhani's approach to proving Witten's conjecture is based on hyperbolic geometry. Of moduli spaces. As we have discussed, each genus G surface for genus at least 2 can be endowed with a hyperbolic metric of constant negative curvature, of constant curvature -1, and moreover there is a huge variety of these metrics, and these possible metrics are in one-to-one correspondence with complex structures which agrees with these moduli spaces of algebraic curves. Let me denote, let me introduce hyperbolic surfaces with geodesic boundaries. Picture is like that. If we add here that the surfaces has genus G and geodesic boundaries, then we can consider spaces of such surfaces let me denote the length of these boundaries by L1, L2, and so on. So, we consider more complicated objects than before. We started with smooth surfaces or surfaces with punctures. The geodesics at punctures were of length 0. And here we have boundary geodesics of some fixed length. It is important that these are geodesics. These are geodesics. Now, consider the space where G of L1 is a space of such surfaces. It does not possess a complex structure, but it is real orbifold. It is a real orbifold of real dimension G minus 6 plus 2F. This space is endowed with a symplectic form. Its dimension is even, and it is endowed with a let me Fenchel-Nielsen coordinates. And Weil-Peterson symplectic. We have discussed Fenchel-Nielsen coordinates on spaces of surfaces with hyperbolic matrix already. And what are they? We take a surface and we cut it into pairs of pens. hyperbolic boundary with geodesic boundary. Let me draw something simpler. So if we pick some homotopy class of a simple closed curve, then there is a unique geodesic. So we start with a hyperbolic surface with geodesic boundary and having constant curvature -1, we cut it into pairs of pens. And we pick a cutting and can introduce local coordinates. Local coordinates on the space of such surfaces. So let me draw what are these local coordinates? Напомните мне, пожалуйста, что это за координаты локальные, Фенхеля-Нильсона.
Шестиугольник или что вообще?
Ну, из шестиугольника, если хотите, да.
Что разрезали штуку на шестиугольник?
Ну, разрезали, да. Каждую пару штанов мы разрезали на 2 шестиугольника. Но в этих терминах, in these terms, we have a length
можно характеризовать точками на краях, которые являются геодезическими, точку на штанах.
Когда мы склеим, what happens when we glue a surface out of pairs of pens? How we... Да, вот когда мы сшиваем эти пары вместе.
Если мы их сшиваем, то у нас есть имитация, которая... Не имитация.
Ну, во-первых, у нас должны быть одинаковые длины сшиваемых штанин. Мы пока про сами координаты говорим, а не про их преобразование. We are speaking about the coordinates rather than Да, мы можем их склеить, но у нас есть разные способы их склеивать. Мы можем поворачивать окружности при склейке. So, the Fenchel-Nielsen coordinates are the length of the boundary component and the rotation angle. The rotation angle The boundary components. So, at each boundary component where we do gluing, we get two coordinates. So here we have coordinates L1, T1. Let it be phi. Sorry. Tau, I have used tau already for a very different purpose. Let it be phi, therefore. L1 phi 1, L2 phi 2. So, the space of such surfaces is four-dimensional. It has four coordinates. And these are the Fenchel-Nielsen coordinates. If you cut the surface in a different way, for example, if you replace this this simple curve by this one, you will obtain a different coordinates, but on the same in the same local domain. And the Weyl-Peterson symplectic form is the sum of d Li d tau I d phi I over Li. So what we obtain? We obtain a two form on the space, on this space. A differential two form on a theorem due to, I don't know, probably to Peterson or to Weyl theorem. The Weyl-Peterson symplectic form is well defined. So that it does not depend on the choice of the pairs of pens in which we cut our surface. If we choose a different cut, then the coordinates will be different, but the two form remains the same. I must check whether I am correct or not. Okay. Having this two form, we are able to consider its power Wp to the power 3g minus 3 plus n, and it is the Weil-Peterson volume form. У нас это многообразие или орбифолд вот такой размерности. Если мы два формы возведем в половинную степень, то мы получим форму старшей степени. На нашем многообразии. And it is non-zero. Everywhere. And the key point in Mirzakhani's proof is a computation of this, of the volume of, let me denote this. This is something like let me denote this by omega. Computation of the volume, of the Weil-Peterson volume of this moduli spaces with respect to this volume form. Let's make a break here. And we will discuss. I must check whether I have written out this volume form correctly. Maybe I need some modification, but essentially the proof consists in computation of this volume. Okay, let me continue. It seems that I don't need dividing by L here, but instead one should be accurate in defining these parameters phi. This rotation angle is referred to the length, and let it be like that. Okay, now how do these volumes look like in some specific cases? Here I have a small table. So let me okay. Let me denote this by volume G of L1 Ln. So the simplest situation is when you have genus 0 and a pair of pens of length L1 and L2 and L3. So this situation, L1, L2, L3, and this volume is just 1. This space is just a point. For any triple of lengths, for any triple of positive lengths, L1, L2, L3, there is a unique pair of pens. A unique hyperbolic pair of pens with geodesic boundaries of this length. Just a point. L0, L1, L2, L3, a point. Then volume 4 of L1, L2, L3, it is L1 squared plus L2 squared plus L3 squared plus L4 squared over 2 plus 2 pi squared.
And what is
here is 0. These are And one more probably. Just to give a flavor of it. Mm-hmm. So now I am able to formulate the first theorem by Maryam Mirzakhani. This volume is a symmetric polynomial in L1 square, L2 square, Ln square. For the leading term so. Something like that. So, what do we have here? Here we have a symmetric polynomial in these powers, and this is tau 0 cubed. We have genus 0 and 3 boundary components. Tau 0 cubed. Here we have coefficient 1/2, which is tau 0 cubed, tau 1 1/2. And so on and so forth. Here the coefficient is 1/2 of tau 1. Here the coefficient is, this coefficient is respectively the value of tau 1 squared. Nope. It's like that. It's in genus 2. In genus 2, what do we have? This is tau. If we have genus 2 surfaces with, if G equal to 2 and n equal to 1, then 3G minus 3 plus n is 3 plus 1, it is 4. And therefore here we have tau 1 to the power 4. Yeah, tau 4. What should it be? Tau 4. Пси1 в четвертой степени нужно взять. Да, это будет tau 4. This is tau 4. Tau 4 is the leading coefficient here. The coefficient of L1 to the power 2, 2, and 4 to the power 8. Not that, but in all the cases we have just a polynomial. We also see in addition that this polynomial is not only polynomial in Li squared, but also a polynomial in pi squared. The next term contains pi squared, the next term contains pi to the power 4, and so on. It's also homogeneous with respect to, I may add here pi squared. Great. Now, now let me make an attempt to explain how such a theorem could be proven. And in the base of this proof there is a recurrence. Let me call it Mirzakhani's recursion. What does she do? Suppose we have such a surface. We pick one of the boundary components, and we are trying to understand what happens with geodesics emanating from these boundary points in the orthogonal direction. Orthogonal. This is orthogonal geodesic. It happens that there are only 3 possibilities. Returns back, to
Goes to M1, goes to M2, and neither of these 2 options.
sorry?
Можем вернуться на L1, можем уйти на L2, а можем просто бесконечно вращаться.
Да. The same boundary component. First opportunity. Second opportunity. Needs another boundary component. Around some closed geodesic. And here we are lucky, because in the third case there is a theorem by John Bierman in series. I do not remember what is the initial, that the set of starting points of such geodesics has measure 0. It is a counter set. Это множество несчетное вообще, оно чудовищно по размеру. Его мера равна 0. Оно ничего не заметает. And its complement is a disjoint union of a countable set set of intervals. And each interval belongs either to the, consists either of the points of first kind or of the points of the second kind. Because these requirements are open. If we have taken a point which returns back to our original circle, then a close point will return to the same circle. Now let's look more closely at points of the first and the second kind. We have taken a point which emanates in the orthogonally to the boundary component and returns back to our circle L1, and there is a whole interval of points like that. So take an interval maximum interval of points on the first boundary component returning back and take the shortest geodesic among them. Then it is also orthogonal to the opposite side when it returns. Otherwise, we would be able to move it slightly and to make it short. Orthogonal to the boundary component at both ends. And now let me do the following thing. Let me move Unfortunately, I did not manage to find colored chalks. Otherwise, I would draw a picture with the colored chalks, but I did not manage to do that. Let me move my geodesic a bit to the right. And connect these 2 points by a segment of a curve which is close to the boundary component. In this way, I obtain a simple curve, and as we know, in each homotopy class of simple curves, there is a unique geodesic, which is the shortest one in this class. This is geodesic homotopy equivalent. Equivalent to the shortest geodesic to the interval geodesic moved to the right. Let me put it like that. By moving to the right, I mean that I shifted the geodesic and connect by an arc segment which is close to the half circle, to the half of the boundary circle. And I do the same thing by shifting the interval geodesic to the left. In this case, it happens that the corresponding geodesic is exactly the one of the is exactly the one here. So, in this case, I obtain a pair of pens bounded by L1 and 2 geodesics. Alpha 1. This L1. Now, if I cut off this pair of pens, then I obtain a two-dimensional surface which is endowed with a hyperbolic metric of constant negative curvature -1 with geodesic boundary components. Clear? This is the reduction step. this is the reduction step, which reduces computation of the volume. Computation of the volume is taking some integral over some space. I reduce it to taking an integral over a pair of lengths of alpha 1, alpha 2 can vary. I need to make an explicit integration over these two parameters. And the integrand will be some volume forms integrated over moduli spaces of surfaces of smaller genera. Because when I cut off a pair of pens, I obtain either one surface or two surfaces of smaller genera. Clear? Значит, это такая рекуррентная процедура, которая позволяет выразить объем пространства модулей, нашего пространства модулей кривых рода G, поверхностей рода G, гиперболических поверхностей рода G с n геодезическими компонентами границы через гиперболический, через объем тот же самый объем Вейля-Петерсона, поверхностей с меньшего рода. Потому что род поверхности, ну вот здесь вот мы начинали с поверхности рода 1 и с двумя компонентами границы. Если мы отрежем по альфа-1, мы получим поверхность рода 1, но уже с одной компонентой границы. И поверхность рода 0 с тремя компонентами границы. А их объем мы по предположению индукции знаем. Okay. Now what happens with points of the third type? If we start with an orthonormal geodesic leaving the first boundary component, then there is also some interval of points meeting this second component after leaving this point. And among all this geodesics, we pick the shortest one. This shortest geodesic will be orthogonal to both components. At each end it will be orthogonal to the corresponding component. And now we do the following thing. We move it once again to the left, to the right. We move it to the right. But what happens when we return back here, we'll obtain the same second the same segment by move to the left. So that this will be a single this will be a single connected component rather than two components in the previous case. And in this case, it happens that our here we are again at our same. Не очень показательный пример выбрался из-за того, что, ну не знаю, можно было провести как-то хитрее эту геодезическую. Не хочу сейчас.
Но она все равно тоже стягивается.
Ну, важно, что in this case we obtain a pair of pens bounded by by our first boundary component, by some second boundary component, and by some by some homotopy type, by some geodesic of prescribed homotopy type.
А можно еще вопрос?
Да.
Понимаю, что вот в первом случае мы там вот ну, конкретно в такой картинке не могли там отрезать не по альфа-2 равно 0,2.
Могли.
То есть там мог получиться вот такой вот типа цилиндрика.
Давайте, let me try to draw something different.
Если какие-нибудь...
Если мы выбираем самую короткую,
Let me draw this. Let me draw.
Хроническая метрика на шаре.
Давайте возьмем такую геодезическую, которая вот так вот пройдет. What happens in this case? In this case, we must move we must move to the left, return back here, and take this component. As a result, we obtain a geodesic. The shortest geodesic will look like that. Another geodesic on the right will look like that. And this will be alpha 1, alpha 2.
Скорее был вопрос про то, что ситуация вот именно вот такая.
Именно вот такая, да.
Она именно вот такая, просто сейчас. Вот если не знаю, вот я же правильно понимаю, что ну как это объяснить? Вот если у нас вот как где вот штаны расширяются так к границе.
Нет, они не могут. Они не могут расширяться.
Вот я хотел как раз про это понять, что они действительно так не могут делать.
Они не могут расширяться. Не могут границы расширяться. Сужаться могут, расширяться нет.
Как-то из-за того, что метрика гиперболическая должна быть.
Из-за того, что метрика гиперболическая. Из-за того, что метрика гиперболическая.
Чтобы было бы странно, как получили цилиндр.
Ну, потому что давайте возьмем такую же точно поверхность и приклеим ее вот по этим, по этой геодезической и по этой геодезической. Тогда эта геодезическая будет кратчайшей в своем гомотопическом классе. Поэтому она не может расширяться. Она не может расширяться, она может только сужаться. So, and the next step is to express this L1 as the sum of intervals of the form of lengths of intervals of the form either I and in the case I we have pair of pants L1, alpha 1, alpha 2, or the case higher 2 pairs of pants L1, Li, alpha. And what we have to do in order to establish this recurrence, we must sum over all such pairs of pants. So we sum over all pairs of pants containing L1 as one of the boundary components. In this case, we need to make an explicit integration over all possible values of the lengths alpha 1, alpha 2 of intermediate boundary components. In this case, we have to make integration over all intermediate integration. This case requires intermediate integration with respect to lengths let me have a look, maybe I can write down the resulting equations, but probably I will not be able to do that. Okay, let me just write out certain simplest formulas of this kind. L1 these are two terms in the sum. And this 2 refers to the symmetry between intervals. If our geodesic returns back to our original boundary component, then the two intervals have the same length. Each interval это бесконечная сумма. У нас счетное число интервалов. У нас наши интервалы — это дополнение к канторовому множеству, их счетное число. И мы должны по всем таким интервалам просуммировать. Это очень красивая форма. Вообще, как она во всем этом разобралась, я себе с трудом представляю. Единственное, конечно, что она знала ответ. Она знала, к чему надо стремиться. Она знала... Что?
Симметрия потрясающая.
Да. Вот. И давайте я напишу, как вычисляется объем это вот ситуация. Я зря ее нарисовал расширяющейся, она должна быть сужающей. In this case, in the case of genus 1 surfaces with a single boundary component, this formula takes the form L1 equals sum over alpha to logarithm of exponent of L1 over 2 plus e to the power L alpha e to the power minus L1 over 2 plus e to the power L alpha, and it is called the McShane identity. McShane identity. It has been known long before Mirzakhani, and this identity is in fact a generalization of this one for arbitrary genera and arbitrary number of connected components. In this case, we cannot have we do not have the second term because there is no second boundary component. The recurrence что-то не совсем. Сейчас я напишу рекуррентное соотношение. Во-первых, оно длинное, а во-вторых, кажется, все-таки относится к случаю двух граничных компонентов, а не одной. Сейчас посмотрим. Let me write out the recurrence relation, and we will see. L1, L1. L1, L2. Is 1/2. Something like that. Dx. Значит, что важно в этих формулах? Важно, что если мы знаем, what's important about these formulas? If we know that these volumes are polynomials in Li squared, we are able to deduce that this also is a polynomial. Maybe it is not that easy to compute the coefficients of this polynomial, but we are able to deduce that it is also a polynomial. And that's how it works. Well, I have explained, not explained, but gave a hint of how we can prove that these things are indeed polynomials in the length of the boundary components. And what about the relationship between the coefficients of these polynomials and the intersection indices I have mentioned above. So, when we have such a surface and we make L1 tend to 0, L2 tend to 0, and so on, then our surface tends to a surface with punctures. And then one can analyze what happens around what happens when these links are small. And this analysis is by no means trivial. Это совершенно нетривиальное вычисление, геометрическое. And it shows that the leading term indeed coincides with the intersection indices. The leading term indeed coincides with the intersection indices. Well, in fact, it shows more. And let me, I'm going to complete my account of the proof. It shows more. It describes not only the leading coefficients, but all coefficients. And these coefficients are, let me give the complete form of Mirzakhani's formula. It is L1 to the power 2m1, ln to the power 2mn, 2p squared g minus 3 plus n minus m over 2 to the power m g minus 3 plus n minus m factorial. So the absolute value of m is m1 plus 7 plus mn. The leading term is determined by the requirement that this is exactly 3g minus 3 plus n, so that this coefficient is 0. And this is a general case which involves all the terms. And the geometric factor looks like follows. It is integral over mgn bar psi 1 to the power m1 psi n to the power mn times certain kappa 1 to the power 3g minus 3 plus n minus 1. No. And I need to tell you what is this kappa 1, which did not appear, absolutely did not appear in the previous account. Let me return my picture of mg and bar, and we have fiber. This is cg and bar, and we have I don't know, let me denote by psi. The C1, CGM bar. Let it be K. C1 of relative cotangent bundle to CGM and this is an element in the second cohomology of CGN. And kappa 1 is, if this is P, if P star of K squared, whatever it is. Значит, why I'm talking about the things, I'm not going to explain any of this, any part of this picture in detail, but what I'd like to do is to modify, to explain how the generating function can be modified. We have considered the generating function of T0, T1, T2, which is the sum of psi1. This is a generating function collecting all the intersection indices of psi classes. We are able to write down the generating function for these things as well. Let me write it in the form psi1 and 1 psi n mn. T0 to the kappa K0, L1 T0 factorial T1 to the kappa K. T1 factorial and so on, s to the power A factorial, I don't know. Let me K kappa 1. Буквы кончились. Подскажите мне, в какой степени брать kappa 1? Let it be just K. Let it be just K. And without indices, this will be as K over K factorial. Yeah?
Do we have the same power for kappa and S?
what we need is this formula, 3G. Here we have Gn bar, 3G minus 3 plus n equal to L1 plus Mn plus K. That's the relationship. And it happens that this function admits a very simple expression in terms of the original one. So that all this information about all the coefficients in the Mirzakhani's formula for power Weil-Petersson volumes of Weil-Petersson volumes of this moduli spaces is contained already in this function. So that a simple, sorry, what I'm doing, what I'm writing. That's like that.
And then we deduce by S power divided by this power factorial.
Yeah. Sk to the power k. S to the power k. And no, these are not factorials. These are, there are no factorials here. S поделить на единицу, S квадрат на двойку, S куб на тройку. S в кубе, да. So that no additional information in these smaller coefficients of smaller degrees. I don't know who is the first one to discover this formula, but I'm more or less sure that it is Kazarian around 2009. It seems that nobody has published it before Kazarian's discovery. So, indeed, leading coefficients determine completely the behavior of this volume formulas for the volume. Well, I think I can stop here. Let me say that this function is called Witten-Kontsevich potential. And since then it is very popular. It is very popular, and is studied so roughly. Значит, доказательства Концевича, доказательства Окунькова, доказательства Мирзахани, они все разные существенно. И то, что я рассказал сейчас, не дает никакого представления об остальных доказательствах. Вот. Есть еще, ну, наверное, дюжина доказательств сейчас. Формула гипотезы Виттона. Вот. And Mirzakhani's proof is distinguished from the point of view of its geometric insight. Her understanding of hyperbolic geometry and relationship between very different approaches in this geometry between very far domains of mathematics is extremely outstanding. Тут как-то в этом доказательстве задействована огромная куча всевозможных таких эффектов, начиная от элементарных вычислений в гиперболической геометрии самых простых поверхностей, кончая там совершенно головоломными комбинаторными преобразованиями, потому что я рассказал, как в принципе можно сводить вычисление объемов к некоторому рекуррентному соотношению, но для того, чтобы преобразовать это рекуррентное соотношение в то, которое записывается уравнением Картавега-де-Фриза, это тоже требует совершенно нетривиальной работы. И Марьям это выполнила очень изящно. Let me stop here.